ocean, and that larger ocean was the one that he named as Panthalassa. Now, this Pangaea, as per Wagner, had broken down into two larger continents, that is Laurasia, which included the continents of North America and the continental region of the entire Eurasia. And other than that, it also had Gondwana land, which consisted of the regions of South America, Africa, India, Australia, and Antarctica. Now, as per Wagner, over a period of time, these individual continents also broke up and they moved away. Now, if you take a look at the analysis or the theory that was provided by Wagner, he had to provide some sort of reason in order to validate what he was postulating. So today we are going to initiate, or today we are going to look into the reasons which were cited by Alfred Wagner. After that, we shall be moving on into understanding why this theory eventually was but later on why it is that this theory in principle served us significantly. We shall also be taking a look at the other theories today, that is the convection current theory, which was provided by Sir Arthur Holmes. We shall also be taking a look at the seafloor spreading theory, which was provided by Harry Hess. And we shall also be taking a look at the plate tectonics theory. It is the plate tectonics theory which came at the last, and plate tectonics theory took some bits of positives from continental drift, from convection current, from seafloor spreading, and that is what makes the plate tectonics theory the most acceptable and the most possible theory which is prevalent, and it is still acceptable today. So up till that point of time, just keep on observing the various different theories. What do they talk about? One by one, we shall be discussing each of these theories, the basic fundamentals of each of these theories, and then all those theories will lead us to the aspect of the gist, and the basic positives of all these theories will eventually lead us into the into the plate tectonics theory. And that is where we shall be analyzing in greater detail regarding why is it that the present day landform emerges or appears the way it does. We shall also be analyzing how is it that the mountain ranges of Himalayas have been created. If we say that India was a part of the Gondwana land in the southern hemisphere, how is it that the Himalayas got into existence? All that portion we shall be taking a look today in today's session. Having said that, today's session again is going to be very, very instrumental in terms of the number of questions that have been asked from this particular area. Very frequently, UPSC does ask a question about this in the portion of prelims or in the portion of the mains examination. So that is where we are going to analyze it in significantly greater detail. Now, after this, first of all, we shall be taking a look into the assumptions which Wagner had taken. So there we were very clear when we studied it on Tuesday that Wagner had made certain assumptions. And the assumptions were very simple. Assumptions. Megha, we will talk about that possibility as well. The question that is asked by her is that, is it possible that all the continents get together again? So that is a very realistic possibility, and that is something which we will later on look at as the part what we refer to as the Wilson cycle. Okay. So the assumptions made by Wagner. So here, when we talk about the assumptions made by Wagner, Wagner had made simple assumption. The first is that structure of Earth, as we had discussed earlier, structure of planet is divided into Sial, that is the crust. That is a portion of the crust. Sima, that is the portion of the present day mantle. And Nephi. Then he went on to had another assumption, and that was basically continental land masses are floating freely over oceans. Okay. Now here, when we talk about the second assumption that the continents are floating freely over oceans, now I want you to understand one basic principle here. And the principle is about flotation. Many of you are not from a science background, so many of you will have a doubt, even though this this portion of science regarding flotation is something that we study in class 6 to class 8. But nonetheless, let us assume that we don't know this principle of flotation. Now, when any object floats, let's say on water, is there a force acting upwards or not? What do you think? When you have any object which floats on water, is there a force acting upwards or not? Yes, there is. Basically, you can imagine it in the sense that suppose you have a sheet of thermocol, right? A thin sheet of thermocol. Now you put it on a bucket of water, it will float on water. Now do one thing with your hand, put out a force whereby you try to deliberately sink that sheet of thermocol. You will observe it immediately is pushed up and starts floating. That force which acts on any floating object, whereby the floating object displaces its own weight in water, that is referred to as the force of buoyancy. Yes, it was given by Archimedes and is referred to as the Archimedes principle, but many of us are not aware of that. Now, here, basically, the aspect is, Anubhav, when I'm talking about Sial and Sima, this was the assumption made by Wagner. Okay, this is not the aspect of what is present today. All of you, please understand, when you analyze this theory of Alfred Wagner, this is a theory which was given in 1912. Please don't compare it with the present day knowledge that you have. This theory is significantly older. Realize it when we talk about plate tectonics, then judge it on the basis of what is present today or not. This was the assumption made by Wagner much earlier. Okay, so have that clear cut mindset. Okay, now here, when we talk about the force of buoyancy acts on any object which keeps on floating. So as per Wagner, continents are floating freely over the oceans. That means the oceans would exert a force of buoyancy on the continental land masses, which meant continents experience the force of buoyancy by the oceans. Okay. Now, this was the second one, was the assumption that Wagner made out of his own. The first assumption, as we have already seen in the last class, was simply borrowed from the idea postulated by Edward Suess, the Austrian geologist. This was borrowed from internal structure provided by Edward Suess. Okay. Now, this was the assumption that he made. Now, here itself you can analyze that his assumptions were incorrect, in the sense that continents can never be floating over water body. If that would have been the case, continents have moved anywhere that they would like, but that is not the case. So in his assumption itself, some amount of flaws did exist even at that point of time, but nonetheless he used the assumptions in order to suggest the continental drift which was happening, and in order to provide the reasoning for the same. But when you provide a reason for the theory, any kind of reason for the theory, let's say, that you provide, now hereby, let's suppose you have a particular theory where you say that earth behaves in a certain way. Now you have to prove that why the earth behaves in a certain way. So Wagner had said that the continents, they do drift. Now the basic job was to prove that how is it that you can say that the continents do drift. So before Wagner, as per his evidences that he provided, as per the various different sets of parameters that he used, Wagner had two problem statements in front of him. One was to prove that North America and South America, which were once a part of Europe and Africa, these are the two continents which are moving away from Europe and Africa. This was the first problem statement that he wanted to prove. So the problems, or rather, to prove, what? To prove A, the movement of North and South America to the west of the present day. So to the west of Europe and Africa, they are moving westwards. So to prove westward movement of continents shown by North and South America. And second thing that he wanted that the continents indeed do drift is basically the aspect regarding, is my voice audible to all of you? Is the voice, yeah. The second thing that, perfect, thank you guys. So the second thing that he wanted to prove was basically that from the region of Gondwana land and Laurasia, where you had large continents in the polar region, now if you take a look at the present day shape and size of the planet, you will find that India is pretty much to the north of equator. Africa has pretty much moved north away from the polar region that it once was supposed to be in. Australia is moving northwards from the earlier position that it was supposed to be in. Even South America has moved northwards from the earlier position near the South Pole. So as per Wagner, all the continents were initially very close to the poles. Now they are moving away from the poles. So the second point and the second fundamental that he wanted to prove was movement away from poles. And this is something which was referred to as, this was cited as flight away from poles, which in German he also named as Polflucht. Very good. In German, he named it as Polflucht. Okay. Now, these were the two problem statements that Wagner went out to prove. Now, he gave two reasons in order to support or in order to provide solution to both these problem statements that confronted him. So, in order to prove westward movement of continents, or In order to prove westward drift, Wagner cited the reason. What was the reason? The reason was tidal force, or the gravitational force by sun and moon on earth. Okay, this was the force that he cited was responsible. How? So basically Wagner said that, look, you have planet earth. Planet earth keeps on rotating around its axis. You also have the presence of sun, right? You have the presence of sun, and you also do have the presence of moon, right? So as per Wagner, you have the presence of moon, you do have the presence of sun, and you have the presence of the planet earth as well. Now he said that, look, both sun and the moon, they will be extending their gravitational pull of attraction, and planet earth continues to rotate in a direction which is west to east. So as per him, the continents are already freely floating over the oceanic masses. So if something is floating very freely, it will be very prone to gravitational pull of attraction. So as per him, that, look, at one point of time, you had the entire continent of Laurasia, right? You had the entire larger continent of Laurasia. Now, and also in the case of Gondwana land. Now, as the planet was rotating continuously and the land masses were also floating, the gravitational pull tried to hold these land masses in their place as the planet continued to rotate underneath them. Think about it. Suppose here you have the planet, this is the moon. So because of the moon's gravitational pull, as the planet would rotate, the few of the land masses, they would be held back, as a result of which not only did these land masses start breaking, but also they followed and observed a kind of a westward drift. So the gravitational pull would hold these land masses, would break them, and would induce a kind of a westward drift. Gravitational force would hold the landmass in its place, lead to breakage, and eventual westward drift. Why only westward drift? Why only westward drift? Because the planet is rotating. So think about it. The planet is rotating from west to east. If something is holding the land masses back, the land masses will lie stable or still in that region as the planet continues to rotate. So if you observe it from the planet's perspective, if let's say you are an individual standing here, so for you it will appear as if it is moving westward, but in fact, as per Wagner, this is being held up by the sun and the moon. So this was the first reason that he cited. The second reason that he cited was basically the polar fleeing force. Second reason was polar fleeing force. In order to explain that you do have the presence of or you do have the activity or the observation that he made that all the land masses, they are moving away from the poles. In order to explain that, he used the term polar fleeing force as the second reason. So the first reason, what was the first reason? The first reason was the simple aspect that the gravitational force extended by or subtended by sun and the moon, that is strong enough to hold the land masses which were floating in its place and thereby ensure a breakage and subsequent detachment. And that landmass being held in its place, it appears as if it is moving westward. Now he used the first reason in order to prove something else. He used the first reason in order to explain the formation or the presence of many chain of islands that you have in the Atlantic, in the Indian Ocean, across the region of Japan, etc. You would observe that you have a larger landmass. On the sides of it, you have islands. For example, if you take a look at the Caribbean islands in the Atlantic, that is very close to the eastern coastline of North America, but it is separate. So thereby he said that, look, when the land masses were getting detached because of this force of gravitation, all the land mass could not be held together and the land masses started breaking, creating a chain of islands, or what he referred to as island arcs. So he used this in order to explain as the land masses or as the continents were moving west, all the land masses could not move at the same pace, same speed, thereby breaking and creating islands. Example that he used the example of Caribbean islands. Okay, so this was the aspect which was utilized or which was provided by Wagner for the tidal force. Now, when it comes to the aspect and regarding the formation that the land masses, they are moving, they are breaking, why they are breaking, why they are moving, we'll come to all of that. As of now, just try to understand what Wagner had said and what was going on in Wagner's mind. What is it that he said as the reason that he provided? Okay, so the second one was the polar fleeing force. The polar fleeing force led to the movement of the land masses away from the polar region. Now this, he said, is a resultant of, it is a resultant of two forces, of two forces. One is centrifugal force and the other is force of buoyancy. Force of buoyancy. Now, he said that, look, you have planet Earth, its shape is not a perfect sphere. Planet Earth is having a shape which is somewhat bulged around the region of equator, right? Or let me use this. It is having a shape which is slightly bulged around the equator. Now, what do we mean by centrifugal force? What is the meaning of centrifugal force? What do we mean by that? So when any object moves in a kind of a circular motion, Whenever there is a kind of a repeated circular motion with a great speed, the object experiences a force which tends to throw it outside. Ever if you have tried to ride a bicycle or a scooter in closed circles at a quick pace, you will feel that you have a tendency to fall on the outside as well. That is the centrifugal force. So any object which moves in a kind of a rotational motion, right? Any object which moves in a rotational motion around a central or a circular path, that object will feel a force acting on the outside, that is the centrifugal force. Now, in the planet Earth, as the planet Earth is rotating, its radius is going to be significantly more around the region where? Around the region of equator. Why? Because the planet is bulged around the region of equator and is flattened near the region of the poles. So naturally and normally, when the planet keeps on rotating and moving from a direction of west to east, the centrifugal force which will be acting on this planet will be acting on the outside around the region of equator, right? That will be the force which shall be acting. Now, as a consequence to it, what will happen? So he said that, look, continents are already floating, continents are floating and they are experiencing force of buoyancy, right, which is pushing them upwards. Then there is another force acting on the equator which tries to push things on the outside. So naturally, the continents which are present in the polar region, the continents would break and they would be attracted to come to the region around equator, right? He said that the continents would try to break and would try to come to the region around equator. So this was the second reason to explain the flight away from the poles. So owing to the centrifugal force, huge centrifugal force, or rather we can frame it in a different manner, owing to the shape of earth, that is a geoid. When I say geoid, basically flattened at poles and elongated or bulged around equator. So owing to the shape of the earth, centrifugal force would act on the outside at equator. Okay? Then Wagner said that this force, aided with the force of buoyancy, would pull the continents away from the poles, which he referred to as the flight away from the poles. So these were the two reasons. The second reason was that there is a centrifugal force which is acting on the outside around equator. Why only around equator? Because the shape has a bulge around the equator. That is where you have the largest radius, and that is where, as the planet is rotating thereby around equator, you have a circular motion which is significant, and you have an outward force, that is the centrifugal force. So that outward force, along with the force of buoyancy, would basically bring the continents away from the poles near the equator. These were the two reasons which were provided by Wagner. Now, both these reasons that were provided could very well explain what he wanted to suggest as a theory. But were these reasons correct? Were these reasons legit or legitimate overall? So for a long period of time, that is for a few years, Wagner's theory was not even accessible to the rest of the world, because this theory was written in German. This was postulated in German. It was much later that the English translation became available, and that is when the world critically analyzed this theory. Now, if you move ahead with the analysis of the theory, thereby you have, whenever you carry out the analysis, you have two portions of the analysis. That is drawbacks and also the positives. First of all, let us take a look at the drawbacks. Now, here, when you talk about it, so basically the basic assumption that was made by Wagner, that the planet Earth's interior is divided into Sial, Sima, and Nephi. That is not the present day context. That is not reality. While the core is Nephi, but significant portion of the crust also has got silica and magnesium. That is the oceanic crust. So it is not the mantle which is referred to as Sima anymore. So that assumption was incorrect. The second assumption that he made, that the continents are floating freely over the oceans, that is absolutely incorrect. That cannot be possible, because when we have studied the crust, we have seen that you have the continental crust and the oceanic crust is also present. It is not as if the continents can freely float. So the drawbacks, both assumptions were incorrect, right? Whereby internal structure of Earth cannot be divided with mantle being Sima. Then the second reason, assumption that he made, continents would not, or rather, continents do not float. So both the assumptions that he made, both the assumptions were absolutely incorrect. Then, thereby, when he provided the reasons, the first reason, that the gravitational pull of the sun and the moon is what is breaking the continents, and that is leading to the westward drift. But in fact, had the gravitational pull of the sun and the moon be so strong that they would be able to break the continents, hold the continents in their own place as the planet would rotate, then that huge amount of gravitational pull would have brought the rotation of the planet to a standstill within 50,000 years itself. So obviously, the gravitational pull extended by both of them is not that huge. Okay, so gravitational pull subtended by moon and sun are not strong enough to break the continents. Had it been the case that the gravitational pull would have been so strong, planet Earth would have stopped rotating within 50,000 years. But that has not happened. Planet Earth has been rotating for billions of years. So obviously, this reason that he provided was incorrect. Then, the second reason that he said regarding the pole fleeing force, which happens because of combination of the centrifugal and the force of buoyancy, thereby no such force of buoyancy acts upon the continents, as they are not floating devices or floating land masses. Right? So as you can see, even the second reason that was provided by Wagner, that also was incorrect in the sense that such force of buoyancy does not act or cannot act. So what does that mean? That means that other than the evidences that he provided to support the continental drift, the assumptions, the reasons, all of them that he provided, all of them were incorrect, right? So because of these drawbacks, the continental drift theory was rejected. It was rejected whole and soul. But then, does that mean there were no benefits or no positives of this theory? No. This is the theory, or this was the first theory, which for the first time opened up the imagination for the world that indeed the continents could move. Yes, indeed, the continents would have moved. That is why you had such evidences. It is a different matter that Wagner could not provide the correct reasons why they could move. After all, he was a climatologist, he was a meteorologist. So his expertise was never in the aspect of land masses, crustal portion, etc. But the basic part regarding the continents could move, that was provided in a significantly complete manner for the first time. And that in itself opened up huge possibilities. Before that, everybody, when they provided the model of the planet, they talked about various theories that or what was referred to as the contractionist theory, that the planet is contracting quite significantly as it is cooling, due to which you have such shapes of continents and oceans. Those were absolutely ridiculous theories. But then Wagner, for the first time, opened up that horizon of thinking. So, for the first time, he opened up the possibility of continents drifting and moving with respect to each other. Now, his was the first theory which even talked about the creation of the island arcs, the Caribbean islands, for example. The theories before him, they never even offered any kind of explanation regarding the aspect of the creation of islands. They never even talked about it. Wagner had also, by the way, said that look, as the continents are moving to the western part, these land masses, they are experiencing some amount of friction from the water body and the oceans, and that is why the land is folding to create a kind of a fold mountains along the west. Thereby, he tried to explain the formation of Rockies and Andes, which were present, which are indeed present on the western margin of North and South America. So, thereby, he said that because of the force of friction which is experienced as the continents are moving westward, that is why the land in itself, as it is moving, it is experiencing friction and the land is folding. So, he talked about the existence and origin of fold mountains. Example, Rockies and Andes. This was again done for the first time, right? So these were few of the positives, and basic positive was the most major positive. The theory led to the development of further theories such as plate tectonics. That is the biggest positive. But nonetheless, the theory of continental drift, that was rejected, that was discarded. And the entire perspective was kept in a back burner. It is a different matter altogether that almost around 40 years later, after Wagner's death, the plate tectonics theory also talked about something on a very similar lines. And it was after the plate tectonics theory was postulated that people got an idea that yes, indeed, the evidences that Wagner had provided, that carried weight. Even though the reasons and the assumptions that he made, they were absolutely wrong and incorrect. They could not stand the test of time. But the basic idea was in place. The basic idea that yes, at one point of time, North America and Europe would have been together, Africa and South America would have been together, and later they have drifted. That basic idea was correct. Wagner did not have the clue to prove what he was saying, but what he was saying was correct. So that is something we got to know much later. This was a theory which was provided way back in 1912. At that point of time, our understanding regarding the Earth's internal structure, our understanding regarding volcanoes, earthquakes, everything was significantly limited. But still, you can extract positives out of this theory. It was in the 1920s when you had another theory which came up regarding the aspect of movement. Now, this theory did not talk in great deal about the formation of land masses, movement of the or formation of various mountains, islands, etc. That was not talked about this theory. This theory was basically given by Arthur Holmes. This was provided by Sir Arthur Holmes. So, what was this theory about? If you take a look at this theory talked about the process of convection. Now, what do we mean by this process of convection? Suppose you take any utensil at hand, right? Let's suppose you have at hand. Now, this utensil, let us suppose you fill it up with significant amount of water, right? And you try to boil water. This is something that you would have observed on a day-to-day basis, even at your homes. When you try to boil water or milk, would you observe? Straight away, does the water start boiling? Straight away, do the bubbles start appearing? No. You have heat which is provided at the base, due to which the lower portion, let me represent it by different color, the lower portion of water gets heated. And that is where the bubbles are created. These bubbles eventually being lighter, they rise up through the liquid. And eventually, they rise to the top, creating a vacancy at the bottom, which is then filled by colder water from top, which replaces that. So there is a kind of a continuous current. This is the manner in which heat is distributed. So this is what was cited by Arthur Holmes as the convection current. And he utilized this convection current, which we generally observe during the heating processes, to explain what goes on inside the planet Earth. Now, he explained something very simple. He basically explained, if you take a look at what he wanted to say, he said that, look, planet Earth has got a lot of residual heat, right? It has got a significant amount of residual heat which is prevalent. You have the core. Now, he said that this residual heat which is present in the region around core, you have huge amount of residual heat. Residual heat. What is residual heat? We have looked into it significantly in the previous class itself. What do we mean by residual heat? It is basically the heat which is present in the interior of the planet, which is trapped in the interior of the planet since the time of its formation itself. Because the process of cooling was initiated from the outside, so the heat remained trapped in the inside. This is something that we saw in the second class itself. So I hope that you guys are also revising it. You guys are not simply sitting and attending the class as if you are paid to do so. Okay, I hope that you guys are revising it, because in the portion of geomorphology, climatology, if you don't revise, the concepts will come hard and fast at you, and thereby you will lose track of what is happening. This is what happens with majority of the candidates. They will come across a certain particular topic where they have the habit of not revising or reading what has been done earlier. It is my duty to attend the session at 5. At 5 I will open up, I'll see what is being taught, and later on we will see, because we are so smart enough. Now a topic will come where the previous concept is being used. That is where they will find some amount of difficulty, and immediately they will get decoupled with the subject, and they will pick up easier subjects available in the market. For example, when you get bored out of reading geography, the easiest temptation which happens in the mind is, let us study some part of history, let us study some parts of polity. So that is what happens with most of the candidates. So I hope that you guys do maintain. It is the initial portion of the sessions, so I hope that from now only you guys do inculcate the habit of revising what has been done in the previous class. Okay, otherwise it will be very difficult for you to build up the concepts. You will be a mere spectator out there. Okay, so this residual heat, he said, was present in the planet Earth since the time of its formation itself. Right? So that huge amount of residual heat simply acts like the burner that you have when you heat the liquid in general. Now he said that, look, this huge amount of residual heat, it will heat up the mantle, the low portion of the mantle immediately above the discontinuity which is present between mantle and core. Now let me ask the question again. What is the name of the discontinuity present between mantle and core? Very good, guys. No, few of you have it. It is the Gutenberg discontinuity. Okay, it is the Gutenberg discontinuity that is present. So the around the region of Gutenberg discontinuity, you have enough heat which is produced that heats up the portion of the lower mantle. As the portion of the lower mantle gets heated, thereby that heat is then transmitted to the upper layer. Then that heated portion will heat up the other region. And in this way, simultaneously, heat is basically transferred upwards. It eventually has got a kind of a divergence, and thereby it also, just like a basic convection current, this heat which is provided by the outer core also completes a convection current. So this was the theory that was provided by Arthur Holmes. That huge amount of residual heat generates a convection current in the mantle. Generates a convection current in mantle. Okay. Now, due to this convection current, Arthur Holmes was absolutely convinced that when you have a convection current like this, which is pulling in opposite direction, this would lead to a kind of a pull away in the case of the land masses. The land masses would be pulled away from each other. And wherever you have the convection current which sinks down, thereby it would also pull the land masses to the downward direction. But he did not postulate this theory quite significantly. He did not explain this theory in terms of the land masses. All he wanted to suggest what there indeed exists a convection current in the mantle. And this convection current has got a horizontal component which pulls away in both opposite directions, and a vertical component as well which sinks. So this convection current has got vertical component and horizontal components. Okay, both the vertical and the horizontal components would be present of this convection current theory, which would pull the land masses away from each other, and wherever the convection current is going down, it would bring the land masses along with it. That was the aspect which Arthur Holmes talked about, because his theory did not elaborate about which part of planet Earth is he talking about, which land mass is he talking about. That is why his theory was not analyzed in further detail, but then he did provide a very basic chunk which helped further in the development of the later plate tectonic theory, as we will look into, and that is the aspect of this convection current which would be present in the mantle. Why would the convection current be present? Because of heating which is provided at the lower mantle. Why is there heating provided at the region of lower mantle? Because of huge amount of heat which is present in the outer core. Why is there huge amount of heat produced in the or present in the region of outer core? That is a result of the residual heat which has been trapped in the interior since the time of formation. Why is it that the residual heat is trapped in the interior since the time of formation? Because the process of cooling, as we have seen, was initiated from the outside. So everything started solidifying from the outside, trapping significant amount of heat in the interior. Okay, so that is the aspect of the theory of convection current. Now, this was provided in the 1920s. Now, significant decades passed, but no further development had taken place. And this continued, and very soon the world was staring at World War II. The 1940s came, the era of great inventions had already begun. By the 1940s, by the late 1930s and early 1940s, Germany, who was quite a significant force to reckon with in this World War II, Germany had developed a modern machine, the machine that was referred to as the weapon that was referred to as U-boats, that present day we call as submarines. So these submarines were developed by Germany. These submarines could stay underwater, and successfully they would target the British and the American passenger as well as the vessels carrying supply for the troops. The British and the American forces were significantly reeling and significantly suffering from the impact of these U-boats, German U-boats. France and the French Navy had already basically experienced humongous amount of losses at the hands of these German U-boats. So in the 1940s was initiated the development of newer systems which could look underwater, which could look under the oceanic water and thereby would track these submarines. Now, when I say look under oceanic water, am I talking about a camera by which somebody could look at it with their eyes? No, because at a depth, oceanic water is absolutely dark. So how would you look under the oceanic water? With the help of sound waves. And I'm sure all of you would have heard about sonar equipments, etc., whereby sound waves are emitted from the ship, and those sound waves, they hit the ocean bottom, various parts of ocean bottom, and they are reflected at different rates dependent upon at which depth do they get reflected. These reflections were then analyzed, and accordingly it was figured out that where is it that a submarine is present, where is it that the ocean bottom is present. This work began to be carried out very soon. Many German submarines, many German U-boats were hunted and were put out of service, thereby providing significant amount of relief to the naval forces of France, Britain, and America. But then, after the war ended in 1945, all the navies had started developing these sonar equipments. These equipments were already in use in humongous proportion. What to do with them? So, thereby, these equipments were then utilized in order to explore the ocean bottom. Because by the time the Second World War had ended, few people had started getting the idea that, look, ocean bottom is not what we thought about. Because at that point of time, the predominant and the prevalent thinking was very simple. It was that the ocean surface looks flat, the ocean bottom must also be flat, right? Nobody had thought about what the ocean bottom looks like, where the ocean bottom exactly lies. But during the World War operations, few of the naval expeditioners, they got some clue that the ocean bottom is nothing or is nowhere close to being flat. Now, as the war ended, significant researches began to be carried out with the availability of these modern machines. One such American naval expeditioner was Harry Howard Hess. Now, Harry Hess, basically, he studied the ocean floor. Now, when Harry Hess studied the ocean floor, he basically started observing a variety of features. To his surprise, he found out that the ocean floor is not at all flat, but rather it has got underwater mountains, it has got underwater trenches, and it has also got underwater ridges. What do we mean by ridges? Ridge, when we refer to, is a slightly upraised area which is present, which has got a significant kind of a slope. He observed that. Then, furthermore, Harry has observed his initial study was carried out off the coast of California, that is near the Pacific coastline. But further studies that were carried out, based upon that, Harry Hess made certain observations. He observed that the region of the Atlantic that indicated something very, very unique. And the region of the Atlantic indicated basically that the mid-oceanic ridge which was present, that was a zone of active volcanicity. The mid-oceanic ridge in the region of Atlantic that frequently experienced volcanic activities. And he observed, Harry has observed that basically such volcanic activities, they are present all across the Atlantic Ocean, across the mid-Atlantic ridge which was present. Then, upon further study of the oceanic floor, he found out that as you go to the central portion of the Atlantic, the sediments or the deposits, they are very, very young. They are very new. As you go away from the central portion, closer to South America and closer to Africa, you do find that the sedimentary deposits at the ocean floor, they are very old. He also found a very startling fact that the sediments on the ocean floor are nowhere older than 200 million years ago. They are nowhere older than 200 million years. Whereas, when we talk about the rocks present on the continents, by that point of time, we had known that you had continental rocks as old as 3.2 billion years. So the continental rocks were as old as 3.2 billion years, whereas the oceanic bed was as new as only 200 million years. So he had these observations. Based on these observations, Harry Hess propounded what is referred to as the seafloor spreading theory. Now, as per this seafloor spreading theory, what was this theory exactly about? This theory talked about certain very basic things. This theory talked about the aspect that, look, from the region of or in the region of the ocean, you do have the mid-oceanic ridges. And you can observe here, when we talk about a mid-oceanic ridge, we are talking about an uprised, an elevated area. Across the ocean floor, you have an elevated area. So he did observe that these mid-oceanic ridges, they are zones of active volcanicity. And he said that, look, because of the convection current that was cited by Arthur Holmes, because of this convection current, you have molten materials which come up from the mantle and they create volcanicity. And that is why mid-oceanic ridges have volcanic eruptions. Furthermore, he said that as there is volcanicity in the region of the mid-oceanic ridges, there newer crust gets created. Whereas the older crust, it keeps on getting destroyed at the ocean continent boundary as and when the convection current moves. So the seafloor spreading theory was in fact based upon the basic principles provided by Arthur Holmes in his convection theory and based upon the observations that Harry has made. So what are the observations that he made? So if you take a look at the observation, first of all, the observations were simple. Oceans are not featureless plain. It contains mid-oceanic ridges, there are rises as well, trenches, plains, sea mounts, everything. Now, oceanic rock sample in terms of age were nowhere more than 200 million years old, whereas continental rocks are as old as 3.2 billion years, which means what? This portion implies that oceanic abyssal plain here refers to deep sea plain. Before you guys bombard it in the question portion, it refers to deep sea plain. Okay, all these seamount, etc., all of that you will cover at a later stage. Don't worry about it. Okay, this implies that oceanic crust is much younger and keeps on getting cycled. It keeps on circulating. That is why it could be only 200 million years old. That was the implication of it. That the oceanic crust keeps on getting destroyed and recreated, whereas the continental land masses are as they have been formed. That is why the continental land masses are 3.2 billion years old. Now, near the mid-oceanic ridges, basically it was found out that on the crest of the mid-oceanic ridges, cracks with continuous volcanic eruptions were found. So, near the mid-oceanic ridges, because they are volcanic eruptions, rock sample were younger and near the trenches. That is, where is it that he found trenches? At the ocean continent boundary. Trenches he found at ocean continent boundary. That is where he found it. Okay, I'm not talking about the reality as of now. Forget the reality. What is the reality? But then what he found the trenches near the continent ocean boundary. So he found out that near the mid-oceanic ridges, the rock sample is younger, whereas near the oceanic trenches, the rock sample is much, much older. Which means what? Which means newer crust is getting created near the mid-oceanic ridges, whereas the older oceanic crust is getting subducted or destroyed near the oceanic boundaries. This implies that newer crust is created near the mid-oceanic ridges and older crust is destroyed at continent ocean boundary. Now, this was the basic aspect of it. Okay, this was the basic aspect of seafloor spreading. Now, let us understand it with the help of images and a kind of a picturization or the visualization of the same. So, as per him, basically, if you consider a continental landmass, let's suppose you consider a continent, and this is the continental crust. Thereby, you consider the oceanic crust. Okay, this consider again another continental crust. Okay, now this part obviously will remain underwater. Now, as per Wagner, or rather as per Harry Hess, what happened was that here you had volcanic eruption because of the convection current which is present in the mantle. Now, a couple of you, I'm sure, would have this question. You had said earlier that mantle is solid. Now you are saying convection current in the mantle. Either you were incorrect earlier or you don't know the basics regarding convection current. How is it that convection current can exist in the solid mantle? Please understand, when that much, how is it that heat travels through the mantle? Basically, as we will also take a look at it when we study in the next module about mantle plumes, there also we will cover it, that when a portion of the lower mantle gets heated, immediately it starts melting because of the huge amount of heat. Now, as that portion melts, that heat is transferred to the upper layer, immediately upper layer of the mantle. That portion gets heated, it also melts. So the melted portion slowly and steadily travels upwards because the heat is continuously being supplied. It is not as if someone has put the burner on and put it off. So that heat is supplied continuously, and supply of that heat can be for few million years, can be for few 100 million years, for few thousand years. It changes from one place to another, right? So thereby, this convection current would lead to volcanic eruptions happening at the mid-oceanic ridge. What is a ridge? Ridge is that uplifted or uprised area which is generally present in the region of the any land masses which has got a kind of a slope associated, any kind of elevated portion having a kind of a steeper slope associated. Now he said that, look, in this region you have the creation of a newer crust. Creation of crust. Now, how is it that creation of crust will happen? So, understand this. Basically, suppose you have this, again, I'm talking about what was said by Harry Hess. Suppose you have the oceanic crust. Now, initially, as you have the convection current, this horizontal motion away from each other will pull the oceanic crust away from each other. Now, when the oceanic crusts are pulled away from each other, there will be creation of a kind of a gap. A creation of a kind of a gap will exist. Now, because of this gap, volcanic eruption will happen, and you will have lava which will not only cool down, it will start sinking here and here, right? And it will cool down in this region, thereby forming the crust. Now, when the lava that starts sliding down the elevation, it will push the existing land masses slightly aside, not greatly, but slightly. Nonetheless, the convection current continues. Means what? Means that action of pulling away from each other continues. Means what? Means that at the same area, the crust will again break. How? This time when it will break, you will have the previously created crustal region being a part of both the areas. So the previously newer crust which was created, that will also start breaking. Now, that would mean that there would be newer crust again, which would be formed in this region. And as the newer crust is getting created, the existing older crust slowly and steadily will be pushed aside. This will go on. That is how slowly and steadily. And even after that, if you look at the process continuing, if you have to understand the process, how it continues, after that, it will have a process where you have the older crust, then the one which was created later, okay, the one which was created later, and then the one which was created most recently. All of them also being pulled apart. As a result of that, again, eruptions, volcanic eruptions will solidify and create another new crust. So that is how subsequently newer materials will keep on rising from the mantle and keep on creating newer crust in that area. And as there is a convection current, it will push the existing crust on the sides, where the crust will then go down in the region of these oceanic trenches. What is a trench? I hope that we know the meaning of trench, because you will study about trenches in multiple subjects. Trench warfare is what you study for World War One, etc. Trench is a kind of a ditch that you dig, a kind of a small, a prolonged kind of in-depth digging that you do, right? So which has got a kind of a depth. Now, the oceanic trenches are the deepest point on the planet Earth. I hope that we understand that. The deepest point on the planet Earth underneath the sea surface, that is the Mariana Trench, which continues as deep as around 11 kilometers from the sea surface. That is how deep the trenches can go. Okay. Now, he said that newer crust will get created at the region of the mid-oceanic ridges, whereas the older crust will keep on getting consumed as the newer crust pushes the existing crust aside. So the older crust will keep on getting consumed and getting destroyed at the region of the oceanic trenches or the continent ocean boundary in general. This was the theory of seafloor spreading. I will repeat it once again very briefly. The theory of seafloor spreading basically talks about the fact that you have the existing seafloor. That seafloor in itself is expanding, it is spreading. How is it spreading? It is spreading with the newer crust getting created at the mid-oceanic ridges and the older crust that getting pushed aside. So this was the theory, that the seafloor overall, that is expanding, and the newer crust getting created here and the older crust getting pushed aside, due to which the existing continental land masses of North America and Europe, they are moving away from each other. Okay, so that is what he wanted to say. Basically, he talked about the seafloor spreading, or rather seafloor is expanding due to the creation of newer crust at mid-oceanic ridges and subsequent destruction of older crust at ocean continent boundary in oceanic trenches. This was the theory that he postulated. This was the theory that he put forward. And in this theory, he had taken help of the convection current theory of Arthur Holmes, and thereby he had supported, or he had tried to prove the aspect, why is it that North America and Europe is moving away? Why is it that Africa and South America, they are moving away from each other? But then, his theory also had severe limitations. When we talk about the limitations of his theory does not give a detailed idea about why other continents are moving. His theory does not even talk about the aspect that can the continents break into two. His theory does not explain the small features of the ocean floors, that how were they created. Basically, movement of the continents, and it does not even talk about the lithosphere in general. Now, as per his theory, as the newer crust gets created in the mid-ocean and the older crust gets destroyed at the ocean continent boundary, means wherever you have the presence of mid-oceanic ridges, in that ocean you need to have the presence of trenches as well. That is what will ensure circulation. But that is also not true. So there were severe limitations even to the seafloor spreading theory. But nonetheless, seafloor spreading theory, like the earlier theories, managed to contribute some positives out of it. What were the positives? The positives that the seafloor spreading theory postulated was the very aspect of mid-oceanic ridges being the regions for the creation of a newer crust. Right? That was a huge positive. The second positive was what Wagner had observed, that as you move away from the mid-oceanic ridge, the land masses or the seafloor indicates a similar age. That was later proved by paleomagnetism. That is a different matter altogether. But then, nonetheless, Wagner had said that, or rather, Harry Hess had said that as you move away from the mid-oceanic ridges, in those areas, you have the same age of the rocks as you are equidistant away from the mid-oceanic ridge. So if you are closer to the mid-oceanic ridge, you will have younger rocks. Then as you move away, older rocks. As you move further away, oldest rocks which are available. So these were the positives. Now, based upon these positives, eventually you had the framing of the theory of plate tectonics. But overall, if you analyze this image carefully, this image represents the presence of mid-oceanic ridges. Mid-oceanic ridges. Right? Now here, analyze the region of the Atlantic Ocean. You would observe a kind of a faint, light bluish line all across the central portion of the Atlantic. That is nothing but a mid-oceanic ridge. So this is where the sea floor is indeed expanding. That is why North America and South America, they are moving away from Europe and Africa. Right? But not everywhere do you have the oceanic trenches which are present. Oceanic trenches are limited to certain parts of the world, around the Pacific, around the Indian Ocean. That is where you find majority of the trenches in existence. Here as well, you find a significant trench in existence. Right? So that is where his theory also had certain limitations. So the seafloor spreading observed by Harry Hess, an American geologist, it corroborated the fact that the continents, they do drift and form the basis for the plate tectonic theory. It was the first comprehensive theory which was present, which for the first time talked about movement and formation of seafloors. Formation of a newer crust was talked for the first time, was thought about for the first time by this particular theory. Now, simultaneously, other scholars such as Mackenzie and Parker, Morgan, even Tuzo Wilson for that matter, they developed a more comprehensive understanding of the movement of different parts of the Earth's crust and its related formation. Thereby, they explained it under the theory of plate tectonics. Now, this gave rise to what we refer to as the theory of plate tectonics. Now, the name plate tectonics, here the term tectonics is taken from term tectonique, which refers to or which means the act of building. And when we talk about plates, what do plates refer to here? So basically, as per the study carried out by the various different scientists and geologists, the entire lithosphere. When we talk about lithosphere, what do we mean by that? Lithosphere refers to the portion of the crust and the solid portion of upper mantle above the asthenosphere. Okay, so that is meant by lithosphere. So lithosphere is divided into various smaller portions. That was referred to as plates. So when we talk about plates, so lithosphere, that is the portion of crust and solid mantle, upper mantle above asthenosphere. Okay, so lithosphere is divided into smaller portions known as plates. Now, how did we come to know that what is the division? Where is it that the lithosphere is broken? Where is it that the lithosphere has got a subpart, etc.? That was understood after a careful and a prolonged study of earthquakes and volcanic eruptions. It was found out that earthquakes and volcanic eruptions across the globe, they follow a set pattern. They are observed in certain areas of the planet only. They are not observed randomly anywhere. There's a kind of a pattern to it. And that is what gave us an idea that indeed here you have the entire lithosphere in itself having a subpart which we refer to as plates. So when we talk about plate tectonic, here this theory talks about the aspect that lithosphere is broken into plates. This plate moves over the semi-molten mantle. Which portion of semi-molten mantle are we talking about here? It moves over the semi-molten, very good, semi-molten asthenosphere. Asthenosphere. And thereby, the plates, they keep on moving in respect or with regards to each other, whereby the plates can move towards each other, they can move away from each other, they can move in a manner which is parallel to each other, but they keep on moving. Now here, the question arises is, why will the plates move? It is okay to understand that the lithosphere is subdivided into smaller parts that we refer to as the plates. But why would the plates move with respect to each other? So if you think about it, regarding the aspect of the plate movement, first of all, look at what do we mean by these plates. This represents the various different plates in existence. Now, plates have been divided into two types. Plates have been divided into two types. That is major plates and minor plates. Okay, major plates and minor plates. Now, major plates being the large ones, the minor plates being the smaller ones. So when you talk about major plates, for example, take the case of this North American plate, right? It is a very large plate. Take the case of the South American plate, again a very large plate. Take the case of the African plate, again a very large plate. Eurasian plate, again a very large plate. Now in all these plates, you would find one common characteristic. What is that common characteristic? That these plates can have both continental as well as oceanic crust in existence. So, plates can have both continental and oceanic crusts in existence. If you consider all the larger major plates, there is only one major plate which is completely oceanic. And which is that plate which is completely oceanic? It is the Pacific plate. So the only major plate to be having only oceanic crust. Okay, the only major plate to be having only oceanic crust. Otherwise, in all the plates you will find the presence of both continental as well as oceanic crust in existence. Now, if you observe this image carefully, you would observe certain arrows which are drawn, certain arrows in all places which are drawn. Everywhere you would observe. Now, this indicates the direction that the plates are moving in. Across the Atlantic Ocean, you would observe that there are arrows which are present across here, right? And there are arrows which are present here as well. You have the smaller plates such as the Caribbean plate, Cocos plate, Juan de Fuca plate, Nazca plate, Scotia plate. These are the smaller plates. Now the question arises is, why is it that the plates will move? Why is it that the plates have any kind of motion whatsoever? The answer again was provided by Arthur Holmes almost 50 years back. Arthur Holmes had given the convection current theory. And as per the convection current theory, there is a presence of residual heat which rises time and again from different portions, and that gives rise to a convection current in the mantle. But what happens after that? How is it that the plates will move? In order to understand that, you have a simple experiment again. You can bring it on or you can perform it in your houses as well. A very simple kind of an experiment, if you will observe. So let's suppose you have a larger pan. You fill it up with water. Let us assume you have a larger pan that you have filled with water. And you are heating it up. Right? Now suppose on top of it you keep 2 blocks of wood or 2 blocks of thermocol at the center and very close to each other, almost attached to each other, not joined, but very close to each other. You name them A and B. Okay? You keep these 2 blocks very close to each other. As the heating is initiated, as the water will get heated, what will happen as a consequence, as a result to it? As a result of water being heated, you will have convection current which will form in that water. Observe this. If you have not observed this till now, observe it today. Suppose, and take this with a simple scenario. If you don't want to use thermocol or wood over water, use any of the lighter materials which can float. Now thereby you will observe that when the water starts boiling, the materials, they are pushed away. That is because there is a convection current at play. Something very, very similar happens in the case of plates as well. In the case of the plates also, what is observed is basically you have, let's say, the presence of the crust. Then you have the mantle, and then you have the region of the core. Here you have mantle, and here you have the crust. Now, because of heat which is produced in the region of the core, there is significant amount of convection current which is generated. Now this convection current, straight away, it will hit the crustal portion. Thereafter, this convection current will diverge and will also have a kind of a vertical component associated with it. It will diverge and it will also have a kind of a vertical component associated with it. And that is how the entire convection current will be completed. Okay. Now here, if you analyze what happens when this convection current hits the crust, immediately, because of the huge amount of heat, the crust there starts thinning out. In this portion, the crust starts, because of the heat, the crust starts thinning out in this area. Slowly and steadily, there is also going to be a significant pull which is going to be exerted on both sides of this plate. Right? Why? Think about it again with the experiment that you would have done in your childhood days that we talked about in the previous class as well, where let's suppose you hold a plastic ruler above the flame or any fire source that you have. You will observe, if you keep on pulling the ruler apart, it is not going to immediately break. First of all, it will thin out. As it is getting heated, it will thin out. It becomes very, very thin and eventually disintegrates into two. Something very similar happens here as well. Because of that immense amount of heat, the plate in that particular region, that plate starts thinning out because it is being pulled simultaneously on the both sides because of that horizontal portion of the convection current. So the plate starts thinning out. Right? Now, as the plate starts thinning out in this region, it is simultaneously getting pulled aside as well. The plates, they thin out quite considerably in this particular area. Now, as they thin out, eventually from the nearby regions, water starts coming in because there's a large depression which is getting created. Eventually, this area will be filled with water. But then the process will continue. There will be a pull which will be associated with both sides of the plate because the convection current continues. And thereafter, what will happen? The central portion will widen quite sufficiently, in the sense that there will be a thinning, a further thinning, right? There will be a significant amount of thinning, and in this area, you will have the presence of water. Water will fill up. Okay, it will create a kind of an oceanic region. The plate will break in such a way that it will create a kind of an oceanic region. Furthermore, there is more heat which is continued to be provided by the convection current in a vertical manner. And this eventually will lead to a kind of a volcanic eruption on the sea floor. And this will lead to eruption and creation of a newer crust at the sea floor. Okay, that is how this convection current eventually, or if suppose this convection current, will this be always permanent? No. It depends upon the heat which is concentrated in certain parts of the planet. In certain cases, that heat which is provided, it is concentrated in certain areas for a few 100 million years, and then it diminishes. It can erupt again from some other area. So even this convection current, it has got a variability in terms of its duration. Sometimes it can last for many million years. Sometimes it can be very short timed as well. Now, due to this convection current, there will be pulling apart of the existing land mass. That pulling apart of the, so imagine any particular continent that you see. Let's take the case of any particular continent. Suppose if you imagine Africa getting pulled apart into two directions, right, as it is. So Africa, when it is being pulled apart in both the directions, it will lead to significant thinning of the crust in this area. Now, when the crust will thin out, it will create such a kind of a depression that water from the nearby seas and the oceans, they will eventually fill it up. And eventually, this will be further pushed apart as there is creation of a newer crust at the creation of a mid-oceanic ridges. So this is how you observe here the coastline of the Arabian Peninsula, and you observe here the coastline of the Horn of Africa. Both of them have the same shape, but there is a movement away. And this water which has come in after this divergence has happened, after this movement has happened. So that is how water enters in. However, if there is an existing mid-oceanic ridge, for example, what we see in the case of Atlantic, there, if the convection current exists, it simply pushes the land masses away from each other and aside from each other. That is how the plates eventually they end up moving with respect to each other. So why do they move? So that is because of the convection current from the mantle rising to the surface. So the horizontal portion of the convection current pushes the plates away, leading to divergence or thinning of the existing plate creating or leading to eruptions and newer crust. Okay, so here you get another schematic diagram to represent what happens when the plates they indeed move with respect to each other. Observe, or why is it that the plates move with respect to each other? Here you would observe very basically that initially when you have the convection current which is provided, that provides there is going to be a vertical component of the convection current as well, and that vertical component will push away the existing plates in both sides. Slowly and steadily observe that this plate starts thinning out. It starts changing its structure as well, and eventually you will have here new oceanic crust created at the mid-oceanic ridges, whereas the older plates, they are simply pushed aside. As newer crust is getting created, the boundary which finally got broken, now you see that boundary is absolutely inactive, and it is the newer crust is getting created somewhere very different in the original position where the convection current was to be supplied. So that is why this older boundary, which is no longer observing active convection current, that is also referred to as the passive margin. So this is how the plates end up, and this is why the plates end up moving with respect to each other. So why do the plates move? Because of the convection current. Okay, so the plates move with respect to each other. Now imagine you have two horizontal plates or slabs. Now there are only so many ways in which it can move. It can either move towards each other, it can move away from each other, or It can move in a manner which is parallel to each other, right? So accordingly, when we talk about the various different types of plate movements, we talk about the aspect that the plates, they can move either towards each other, right, thereby leading to what we refer to as the convergent plates, plates moving away from each other, what we refer to as the divergent plates, and also plates which are parallel to each other, what we also refer to as the transform plates. Okay, so these are the basic kinds of plate movements. So these plate movements which happen across the planet, these plate movements give rise to various different types of landforms. Now, one by one, we shall be taking a look at each of these plates. We shall be taking a look at what that happens and what are the possibilities that it leads to, and what are the various different types of land masses which get created. Now, before that, I want you to understand that the plates are moving away from each other due to the convection current. But why will they move towards each other? And of all the things, why will they move parallel to each other? So here, understand this with a simple logic. Suppose you have different plates in existence. Okay? Suppose you have different plates. All of them will have a plate boundary in existence. Let's name them A, B, C, and D. Now, here, if suppose there is a convection current which is to be present in between B and C, if there is a convection current, means what? B and C, they will be moving away from each other, right? That is what a convection current will lead to. Both B and C, they will be moving away from each other. But if you consider A and D, can we not say A and B are moving towards each other? Or A and B are converging and C and D are converging? We can say that. So that is why once you have a kind of a divergence, that can create convergence in some other part of the world, right? So that is why one movement, because the entirety of the planet is divided into plates, one movement across any of these plate boundaries can influence many other plates as well. Okay? Now, here, why is it that the plates will move parallel to each other? So here, the understanding or the basic factor of it is again very simple. Now I take you back to the image of this Atlantic Ocean. Let me take you back to this image. Now here, observe the mid-Atlantic ridge. Now we know that around the region of the mid-Atlantic ridge, newer crust is getting created and the seafloor is spreading. That is something we know. So both the existing plates, they are moving away from each other. They are moving away. And this ridge extends for how many thousands kilometers? Multiple thousand kilometers, more than 10,000 kilometers from north to south. Now, can it be possible that the rate of divergence which is present here to the north and the rate of divergence which is present to the south, can it be possible that for the entire region, the rate of divergence will be absolutely the same? It is not at all possible. If you think about it, absolutely. It will not be possible that for that entire stretch spanning multiple tens of thousand, 10,000 kilometers and so on, it cannot be possible that the convection current is so uniform, the land is so uniform that everything is moving at the equal pace. So there will be unequal amount of divergences, right? You will have unequal amount of divergence. Let's suppose that the northern Atlantic is moving away or is opening up at a rate of, let's suppose 5 centimeter per year. It is moving away at this particular rate. Let us assume that southern part of the Atlantic is opening up at a rate of 2 centimeter per year. Right? Let us assume. So the northern part of Atlantic is opening up at a greater speed. The southern part of the Atlantic is opening at a slower speed. Means what? The land masses, if let's suppose this forms a one continuous land mass or one continuous plate, if the northern part is moving at 5 centimeter, southern part is moving at 2 centimeter per year, there will be friction which is produced. Due to that friction, there will be a crack which shall develop. There will be a significant crack which shall develop, and observe the crack here. This is the mid-Atlantic ridge that we have talked about, where the divergence is happening. Observe the crack which is present. That crack develops as the plate is diverging at a different rate. So that means here the Eurasian plate is moving in the same direction as you have the African plate. But the rate of movement is different. So both these are moving parallel to each other, but one is moving at a greater speed, the other is moving at a slower speed, thereby creating a crack and thereby creating a kind of a parallel motion. So that is how, when you suppose or when you think about it, let's think about it again in another terms. So suppose you have the different plates. Right? Let's suppose you have the different plates. Now, as they are moving away from each other, let's name them A, B, C, and D. If the rate of movement is different, thereby, even though A and C will be moving in the same direction, they will be moving parallel but not together, because the rate of movement is different. That is why when we say that plate movements are of three types: convergent, moving towards; divergent, moving away; and transform, when they move parallel to each other. One by one, we'll study each one of them, and one by one, we will try to understand what these different plate boundaries and what these plate margins are. Okay? Now, after this, we will move ahead. So let's take a break. Yes, we'll take a break, 10 minutes. Take a break, come back, and we continue this. And okay, and then we move ahead.